My name's Zenna. I'm a research scientist at Columbia, and I run a small research organization called Basis. And today I'm going to be talking about inference in causal probabilistic programs using an idea called non-standard interpretation. And hopefully some of these terms will become clear by the end of the talk. So I'm going to talk in three parts. The first thing I'm going to talk about is this kind of paradigm which is emerging called causal probabilistic programming. The second thing I'm going to talk about is program inversion. And then third, I'm going to try to tie these ideas together with this technology called non-standard interpretation or non-standard semantics. Many of the ideas that have been discussed today, I think about a lot. They resonate very heavily with my interests. This talk will be a little bit more kind of grounded in the technology and the systems that we're building. So the first kind of starting point is generative models. So I was looking up the term generative model, and I found the earliest reference to be from the 1950s and by Chomsky and his colleagues, where they were trying to kind of formalize this idea of something which generates, right? In other words, can generate language. And this term has stayed with us for a while, and has been kind of reused and repurposed in different forms of AI and statistics. So I think many people here are familiar with probabilistic graphical models as a kind of generative model. And also more recently, things in AI, now sometimes called generative AI. For example, this image on the right-hand side is a GAN star model, which is generated from noise. So when we look at the commonality between these different representations, one thing that becomes clear is that we can encode all of them as programs, right? We can write down a program for a context-free grammar or a probabilistic context-free grammar. We can write down a program for a probabilistic graphical model. We can write down a program for a GAN or a generative model. And so a recent idea, perhaps 10, 15 years old, is to say, well, what if instead of having these different specific representations of models, we try to say that any program, any kind of thing that we can simulate can be a probabilistic model, right? So think of all the things that we can simulate now in physics, in robotics, in the climate, in pandemics. These are all things that we know how to simulate forwards, but what if we could use these as probabilistic models and use them for inference? So we could go backwards, so retrodict, as I think a term that came up earlier, or infer some latent parameters given some evidence. And so this idea has been formalized and instantiated with a few different tools, and here are some of the examples, like Turing, Pyro, Gen, and Stan. And these are programming languages, or they're kind of embedded programming languages, which you can use today. And the basic idea is that you sit down, you write a model, you encode your uncertainty, and you ask your questions, and the goal of the system is to answer those questions in a systematic way. And I'll explain how this works in detail, but this is some of the kind of pre-existing work which we've been extended with some ideas of causality. So to take an example, so imagine you see this scene. You can think about what happened. So you can retrodict into the past. You can also make some kind of prediction of what would also happen into the future. But you can also ask a counterfactual question, which is, for example, what would have happened had this barrier not been here, right? So I think most people would think, well, if this barrier had not been here, the car probably would have tumbled down the side of the cliff. So my interest as a cognitive scientist is to understand the mental mechanisms by which this takes place. And my interest as an engineer is to build systems that can automate this kind of reasoning. And so the high-level conceptual picture behind these counterfactuals is like as follows. So on the left-hand side, we might imagine some space of possible worlds or some space of possible trajectories. And in the middle image is what we do with probabilistic conditioning. So we add evidence, and this updates our belief about the more plausible trajectories of how the world evolved. And a counterfactual is an interesting construct which combines probabilistic conditioning with causal interventions. So it's basically saying, well, given what I know, which is the middle image, what would have happened had we made this cut or this change into the world? And it's kind of a strange concept, because the counterfactual world is kind of conditioned on or affected by what actually happened in the real world, even though it doesn't really exist in some meaningful sense. And so as has come up earlier in the talk, there's been a lot of work, in the recent decades of trying to formalize this intuition, of our ability to ask these what-if questions and turn them into a kind of a systematic mathematical framework. And one of the key ideas behind this is the causal intervention. So causal probabilistic programming languages, build upon this paradigm which we've seen in our conference, in our workshop so far, kind of the Pearlian approach to structural causality, by instantiating a do operator, an intervention operator, in the context of a programming language, right? And so what this would allow us to do is to do causal interventions and correspondingly counterfactual inference, not just in simple graphical models, but in any program that you can write down in any programming language, right? And so conceptually, we have this operator, which we call do, and the meaning is as follows. So if I say, y sub x equals x, given do, x is assigned to small x, I think there's some kind of syntax thing which is broken. It should be an arrow, not an exclamation mark. What this means is that y sub x is the value of y, had x been set to small x, instead of what it happened to be, right? So let me just show you a very simple example. So suppose we know that x equals 2, and then I say y equals 2 times x. So now I know that y is 4. And so this y sub x, which is y given do x is assigned to 3, has a value of 6. So it's the value of y, had x been set to something different to what it was actually set to, right? So it's a very simple idea, but this is at the foundation of causal reasoning. And a counterfactual combines that ability to do causal interventions with probabilistic conditioning. So now I can say, y given do x goes to x, conditioned on evidence, right? So as we saw in my previous diagram, we can incorporate data back into this model. Okay, so that's this is a very simple ingredient, and we've been building some systems that take this idea and instantiate it into a system that you can use to ask very complex questions. And so my PhD work was on kind of the semantics and the idea behind this, and now we've been building more and more robust systems that capture a wider and wider set of problems that you might care about. And the most recent system is called ChiRho, very, very new, an output from Basis, and I recommend you go and check it out. We've got lots of tutorials, which I'll go through one of right now. So the idea of a dynamical system, and time has come up a lot in this conference so far. And the way that we approach this in kind of causal probabilistic programming is to say, well, let's take any kind of dynamical system that you could express, for example, an ODE model or a PDE, and let's make a Bayesian version of that, and now let's do counterfactual inference with that kind of model. So what I'm showing you on the screen is just a very small code snippet, which is encoding an SIR model, which is a kind of model we use in kind of pandemic modeling, where you've got S for susceptible, I for infected, R for recovered, to denote these 3 different population sizes evolving interdependently over time. And so this is what it would look like, a normal SIR model, the kind of which I'm sure many of you have seen. And then we've got some samples of data, which we're going to condition on. So the next step in using a causal probabilistic programming language is to make it Bayesian. And what this means is taking your parameters, which are normally fixed, and turning them into distributions. All right? So this SIR model has a beta and gamma parameter. And now instead of saying that they're concrete numbers, we're going to use, I think in this case, a beta distribution and a gamma distribution to express our uncertainty about what these values could be. And what I'm showing you here is just a visual illustration of this, right? So we've got a confidence interval showing kind of a belief about the possible values that would kind of be implied over the trajectories given these distributions over the parameters, right? So these very broad kind of wide shaded areas are showing that there's lots of uncertainty about how the system will evolve over time. And then the next thing you do in a causal probabilistic programming language is that you just ask your inference question. You say, well, given this data, now tell me what I should believe about the future trajectories of this system. And the inference system will automatically solve that for you, right? So this is, it's not zero code, but it's a small amount of code compared to what you'd have to do if you wanted to kind of encode this by hand. And the result is the posterior distribution or the conditional distribution or the distribution given the evidence of what we should believe about how the system would evolve given our data, right? And as you can see, from this very kind of broad, high variance distribution, we now have a much tighter distribution. We're more informed about how the world might evolve. So far, I've spoken purely about probabilistic inference, right? I've taken a dynamical system, I've put some priors over the parameters to make it Bayesian. I've used a probabilistic programming system to automate inference, and now I've got a belief about what's called a posterior predictive distribution. But now we want to go into causality and causal interventions, right? So suppose you work in government and you want to know the impact of an intervention on the public. You know, is your lockdown policy going to work? And so the way that we can encode this is to basically impose an intervention over this beta parameter, right? So we can have some function of time, you know, encoding like how much we're going to force the value of beta to vary over time. And this changes our dynamical system a little bit. And for some reason, a lot of these math has got messed up, so you're just going to have to imagine this as a well-formed dynamical system. And then we basically write a little bit of code, right, to encode the intervention that we want to express, right? And again, this is not no code, but it's a small amount of code, and we're including all of the previous code that we've already written. So there's this notion of compositionality that we get. We don't have to rewrite everything from scratch to consider every new question that we might want to ask. In the same way, as a human, I can ask many different questions given my state of knowledge about how the world works. And so this is the inference. The system churns away, and it gives us an inference about what would happen if we were to instantiate this intervention into the world. And what we see you can see on the left-hand side, we have the susceptible, right? And these two bars are showing the period in which we're applying this intervention. You can see that it goes down. You can see the infected rate stays pretty much constant, and the recovery rate, you know, increases, right? So this is giving us some indication that our lockdown policy is going to work. Right? And again, this is the causal intervention, and it's the counterfactual because it's conditional on the evidence that we've seen so far in the world. And we can make things more complex, right? And this is one of the really nice features.
Then a quick question. So
Yeah.
these three populations are considered to be completely distinct, right? With no overlaps and no movement from one to the other over the time scale that you have down there.
Well, they're kind of correlated by the dynamical system, yeah. So they're not independent. They're related in that sense. So they're all part of the same model, yeah. So that's the most basic kind of intervention. We chose some start point and some end point in which we want to apply this intervention. But as has come up earlier in the discussion, there's more complex ways we want to intervene into the world, and an intervention really should be thought of as a model of how people might interact with the world. And so, for example, we might not believe that if we decide to, you know, put in place our policy at, you know, t=1, that the world will respond in the way that we want. And so one of the nice things about a probabilistic programming language is that we can just say, well, let's just set this start time and this end time to be unknown or uncertain, right? So we have some desire to influence the world, but we don't quite know when, and to what degree our policy is going to be adopted by society, right? And so this is just showing the results of this kind of inference, and the results are different. As you can see, there's more variance in the result. And the main point here is that to go from my simple intervention to a more complex intervention is a trivial change of code, whereas, you know, previously somebody would write an entire paper about this new kind of counterfactual inference. And so ChiRho as a system is very new, but we're kind of steadily incorporating more and more kinds of counterfactual and causal reasoning that you might read in papers. And so we've got many examples with quite complex simulations, you know, assessing the causal impact of genes, different therapies on genes. And the grand vision is to incorporate the entire toolset of things that people use in causal inference within a systematic framework that is composable and can be extended to new models, right, and to new methods in a very straightforward way. Okay, so one of the things that arises when you work with simulation models is this kind of likelihood-free inference regime. How do you condition a simulation model? You've got some complex model, it runs for a long time, and in some ways you want to constrict the output of this model to be consistent with some data that you have. And so this is a problem that many people have thought about. If you're kind of very in the weeds of probabilistic inference, there's things like ABC, approximate Bayesian computation, and others. And we've been thinking about this from a programming perspective and from an inverse function perspective. So what is an inverse problem? Well, at a high level, you've got some forward function f and some output output y, and you want to find some input x such that f of x is equal to y. That's kind of an inverse problem in the simplest sense. And so we can say, like, what is program inversion? Well, it's the same thing, but instead of just thinking about mathematical functions, we're going to talk about programs that compute those functions. So you've got some simulator, and it's got some output that we know, and we want to find the inputs that are consistent with that. So let me give you two examples why we should care about this. So one is just in inference in general. So suppose, well, not suppose, the real world is three-dimensional, right? I think we can mostly agree on that. But what we observe as humans is two-dimensional, right? Our eyes are basically cameras. And so somehow as humans, we have the ability to look into the world and figure out the three-dimensional structure of the world given our two-dimensional input. And so you can think about this as an inverse problem, right? Because we understand the forward process which goes from the three-dimensional world to a two-dimensional image. That's sometimes called rendering or computer graphics. That's what powers our video games and the animations we see. But what we want is the inverse of that. We want to go from the 2D to the 3D. So what if we could invert this rendering algorithm? It would then be an inference algorithm. Right? Or in robotics and control, right? We have a forward kinematic function which tells us if I know the joint angles of a robot, it will tell me where the hand is. But what I want is the inverse of that, to say, well, where should I put my joint angles in order to get my hand to this position? And so the first challenge that you'll see is basically the non-invertibility of these functions. Almost any interesting function that you want to kind of use for inference is not invertible. And so in the case of this kind of graphics and rendering, like why is that? Well, one simple reason is occlusion, right? If I had some green ball behind my back, you would see the same thing. And so there's an ambiguity about what is the true reality conditional on the evidence that you've observed. Or even in the case of something as simple as addition, if I tell you that x plus y is equal to 5, you don't know what x and y are. It could be 1 and 3, sorry, 1 and 4, I can add. It could be 0 and 5, right? There's an infinite set of combinations which sum to 5. And so the basic approach that I took to this problem is an idea we call parametric inversion. And it is unfortunate here that the math has got so messed up because it does matter. But the basic idea is to define a generalization of the notion of an inverse. And so if the conceptual understanding is that for any given output of a function, let's say addition, as we just said, there's a set of possible inputs that map to that same output. And let's try to parametrically represent that set. So we're going to define a new function, which we call a parametric inverse, which takes a value in the output of the original function and goes backwards, but it uses a parameter to kind of select between the different possible inputs that map to the same output. So what is the high-level idea? So the high-level goal is that you write down a program in your favorite programming language, whether that's Python or Julia or whatever. Now, instead of running that program forward, you can run it backwards, right? So you can say, well, I know the output and I know some parameters, and that's going to allow me to run this program backwards and choose one of the inputs that map to the same output. So let me just give you an example of what a parametric inverse is. So take addition, as we've been using, x plus, let's say z equals x plus y, or f of x equals x plus y, f of x and y equals x plus y. A parametric inverse of this function will take in a value z, take in a parameter theta, and it will return two values, one for x, one for y. And those values will be z minus theta and theta. Okay. So the point is that z minus theta plus theta is equal to z, right? And the other point is that as I vary theta, I'm getting back all the different combinations of x and y which map to z, right? So now I've got a way to generalize inversion for a non-invertible function that allows me to parametrically select the different inputs that map to the same output. And I can do the same for the square function, and if you think about this, you can do it the same for many of your favorite functions that you use every day. Okay, so I'll skip this slide because it's too hard to read, but that's the basic definition. Okay, so what we've seen is that we can take simple functions like addition or a square root or square function, and we can define these parametric inverses which generalize the notion of inversion. But our goal is to invert complicated simulation models. And so the key idea behind parametric inversion is composition. And that is any complicated model or any complicated program ultimately reduces down to a small set of primitives composed together. That's how programming languages work. That's what allows us to write programs of millions of lines of code. And so the basic algorithm behind parametric inversion is to take a composition, and we'll just start with the composition of two functions, addition and the square function, right? And we'll take that addition and we'll replace it with its parametric inverse, the one that we just defined. And we'll take the square function and we'll replace that with its parametric inverse, and then we'll reverse the order of the composition. Okay? So that procedure is a mechanism to turn a program into its parametric inverse. Right? Okay, and this is just saying that in words. But this is, in some ways, a very large claim. Like, it maybe sounds simple, but I'm basically arguing that you can have a mechanical procedure to invert arbitrarily complex programs. And if you can do such a thing, it vastly expands the space of inference methods that we can develop and the space of problems that we can solve in this paradigm of simulation-based inference. So you should be skeptical. And the reason you should be skeptical is kind of explained by this example. So if I have this slightly more complex function, right, which is just f of x and y equals x, y plus x, and I'm using this green function to just duplicate y before adding it. One of the issues that arises is that if I try to go backwards, I apply the procedure that I just described. I've taken the multiplication, I've inverted that. I've taken the addition, I've inverted that. And I've taken this duplication and inverted that. And I've run the whole thing backwards. One of the issues that comes up is there are some constraints on the parameter spaces that arise on the addition and the multiplication that can lead to inconsistencies if you choose the wrong things. In other words, the parametric inverse is correct, but you might put in some parameter values which are invalid, so it's a partial function. So the procedure that I just described, everything I've told you so far is true. You have a mechanical procedure, an algorithm to invert programs, but it could be the case that it's undefined in some of the parameter values. And so why does this occur? And I think it actually relates heavily to some of the more philosophical things that have come up today, which is that in the forward direction, there's really just like one way to go. And in the backwards direction, there's many choices that you have to make. It's almost like every computational operation, you're making a choice about what to do, and your parameter value is choosing that. And you can choose some paths which are just impossible in the forward direction, right? And if you do so, you'll get stuck, and you'll kind of be doing the wrong thing. And so this gives us a kind of a paradigm for thinking about inference. So normally, if you think about black box-based inference, I've got some model and I want to find some x such that f of x is equal to y. I could do some search over the space of x and I could check, is this equal to y? And I could do some checking. If I get close enough, I'll be happy. That's how approximate Bayesian computation works. With parametric inversion, you have a kind of a different problem, which you actually start with the output, you run it backwards, but you might fall into a different problem, which is that your parameters are not quite what you want. And so we put a lot of effort into trying to solve that problem. And to just say our approach very briefly, we use machine learning to help us find good parts of this parameter space. And it turns out that actually we can generate data sets of inputs, outputs, and parameters, and use machine learning models to help us navigate this parameter space to choose to kind of find the good parts of the space. And also more broadly, and again related to some of the more philosophical issues, it turns out that you don't actually just have to go forward or backwards. You can actually navigate in almost arbitrary direction inside the structure of a model. And this really kind of changes how you think about what a program is, right? A program is really defining relationships between different parts of things that you care about, and how you kind of execute that or kind of run that. There's a lot of flexibility in what you decide to do. Okay, I'm going to step back and just quickly take a broader view, which is that many modes of reasoning can be understood as different kinds of program transformations. But an even more basic question is, what is a program, right? So I'm sure everybody or most people here have programmed, but the way that we think about programming languages in kind of the theoretical community is that a program has some syntax, right? Some kind of well-structured form of writing programs, and it has some semantics, some meaning to those programs. And it has some implementation, a compiler or an interpreter that actually runs those programs. And the way that PR people kind of think about programs is they write these little tables and rule systems to define what programs are. And program transformations are, in my view, this kind of hidden technology which is powering the entire machine learning revolution. So think about automatic differentiation, right, which is essentially how deep learning works. Well, what is it? It's a program transformation. You take in some program and you convert that into a program that computes the gradient. Right? You don't do this. Some system does this. You just write torch.grad or whatever, a high-level thing. But in the background, there's some system which is transforming the underlying program to turn a function into its derivative. So my narrower, broader view is that a lot of the things that we want reasoning systems to do can be understood not just as program transformations, but as what you might call semantics transformations or non-standard interpretations. And going back to the example that I had at the start with 2 times x and so on, the way that this is actually formalized is as a transformation to the semantics of this programming language. Right? So this do operator is taking the normal meaning of a program and changing it in a way such that it makes sense to do this kind of backwards modification of the kind of the parent variables. And so there's been this kind of emerging paradigm of tools like JAX, cassette, enzyme, which are allowing us as kind of inference method designers to implement these kind of program transformations within the same language. And it's opened up automatic differentiation. It's how parametric inversion is implemented. It's how causal interventions are implemented. And I expect many of the more advanced inference methods going forward will rely on this technology. Okay, so to conclude, causal probabilistic programming is a new paradigm that allows you to encode programs or models as programs and automates inference so that you can just ask the questions that you care about. And at least in the idealized world, it automatically computes the answers for you. Program inversion is at the heart of simulation-based inference because somehow you need to find inputs that map to a given output. The next generation of inference methods will not be black box, and by black box I mean just using the input and output. They're going to introspect or inspect into the internal structure of models. And they will rely on program transformations to do so. And finally, there's an emerging class of tools which are starting to mechanize this, which I think everyone should just be aware of. There are many challenges and many difficult things, which I'll be happy to talk about. But this is the end of my talk, and this is some of the stuff that we're working on at Basis, which is a new organization to do just this. So thank you.
Thanks, Zenna. Very, very interesting talk. I realize now that, having learned Lisp as my first computer language, yeah. I think I'm waiting for ChiRho, right? I'm done with the syntax. I have no syntax, and I hate every other language, yes. Okay, questions? Oh, Tim, sorry.
Yeah, so there was a point in your talk when you said you ought to be skeptical, that you can invert certain things. And I think I followed most of what you did, but I just want to check on something about inversion. So there's one way of thinking about the problem of discovering causal structures. If you start with directed acyclic graphs, okay, I have a kind of proposed causal structure. Maybe I have some data that I use to put parameters on these things. Now I've got issues about the noisiness of the data, blah, blah, blah. Okay. But what you immediately find is as soon as you have a bunch of nodes and latent nodes, the number of possible graphs, the combinatorics kills you, right? You give me a graph, I know how to use that to make a prediction. But the question is, can I look at the data and constrain the space of graphs that I ought to be looking at? That's really the inversion that you worry about in terms of causal search. And you can look at this, and you can put in the do operators, blah, blah, blah. But if I'm understanding correctly, the parameter you put in for this inversion, that's going to be pretty restrictive in terms of the sort of functions where that's going to work. I mean, you couldn't do something like that to say, oh yeah, there are lots of different graphs that will give me the same surface statistics. Well, I'm just going to put in a parameter that I can set somewhere to, as it were, resolve that ambiguity. I mean, in a structure like that, this method isn't going to work. Is that correct?
Yeah, so I think there's a few different things that are worth kind of separating, right? So one, in the first part, I spoke mostly about counterfactual inference, which you can think of as a subset of causal inference, less about the problem of causal model discovery, right? Like how do you, as you said, like just take data and construct a causal model. But what you suggested is not impossible. It's just very hard technically to do. And one of the nice things about probabilistic programming languages is that actually you could do just that. So you could write down a distribution over distributions. In other words, you could write down a probabilistic program that generates probabilistic models, right? And then you can say, well, I want to condition that first distribution such that the probabilistic models it generates are consistent with my data, right? So this is sometimes called like a higher order probabilistic model, and it's quite a weird mathematical structure, but it's entirely possible with a probabilistic programming system. It just presents a tremendously difficult inference task, right? And
isn't that constraint that it has to be consistent with the data?
Yeah.
It's almost like a prior, right? How is it different from the prior?
Well, your prior would set up like, yeah, your prior. So what kind of structural or semantic features of the model that you think are a priori likely, but the conditioning would take into account data and say, well, I want my prior condition on data, which gives me my posterior. And in principle, you could use something like parametric inversion to do that. But right now, it would be too hard of a problem to actually do it in reality.
Right. So let me just say, I mean, I understood what you said. There's a big gap between in principle and in practice. I mean, that's where the combinatorics come in, right? You can say, in principle, I could do that, but practical considerations, depending on the search space or the combinatorics, could kill it off as a practical matter, right?
I mean, we've got another entirely different project, which I didn't talk about at all, which is entirely this. Like, how do we search through extremely large structured spaces of programs to find models? And it doesn't yet use parametric inversion, but it's a, yeah.
Next question. No, not Chris.
Thanks so much for your talk. Okay, so this question set up, I think.
Could you speak louder, please? Because we're
Yeah,
recording.
I think this question set up my confusion, so I wanted to ask you about it. So how does the counterfactual part play into the first half of your talk? Like, is it, you mentioned that you condition it on the evidence, and the evidence is the what actually happened. Is that what's going on, or are you using what actually happened as a more strict prior on the models themselves, as in they need to be able to recreate what actually happened, but then we go back and do counterfactual reasoning?
Right. So just to go to this explicitly. Okay, so in this example, right? So this is a counterfactual in the sense that our prior model was this, what you might call a Bayesian SIR model, which is a dynamical system with a prior over the parameters. And this is a combination of probabilistic conditioning and causal intervention, right? The probabilistic conditioning, essentially, like if you read a book by Pearl and others, he'll say this kind of these two steps, right? One, you incorporate the evidence, and then two, you do the intervention, right? And so this is what's happening here. The evidence is the data, right? The infection rates that we saw in the world, and the intervention is this policy that's being instantiated in our hypothetical world, right? If you didn't have the evidence, you would see different plots, right? You'd see
You see fundamentally different shapes.
yeah, you'll see different shapes, right? And so these two parts, conditioning and intervention, are what make, in a particular pattern, are what make a counterfactual. And the program has both of these parts in a very explicit way. I feel like, does that not answer your question?
Okay, so it's a two-part. So first you're conditioning on the evidence, and then you're implementing the counterfactual. But I thought it was going to be asking, what if we had changed the policy? What kind of evidence would we have seen?
Yeah, so that would be, what if you change the policy, what kind of evidence would you have seen? Yeah, I think to understand that fully, I need to see the structure of the question, but it's possible.
Okay, maybe I can give one more clarification. So suppose that you're considering what policies to implement. You implement a policy, and you see the evidence of what happened. And is the counterfactual reasoning not, what if we had implemented some other policy, what would we have seen, so that we can reason about this kind of situation in the future? That's what I was imagining, and in that case, I would say, like, one reasoning that you could do is to say, our model should be able to reproduce the evidence we did see with this first policy because our world followed that trajectory. Does that make sense?
Yeah, so there's a, I'm not certain if this, yeah, this, yeah, there is a kind of a paradigm of like simulation-based check-in, right? You want like if a good model will like reflect the world. You could certainly construct this counterfactual, for example, here, and then see what actually happened in the world, right? And see if your intervention actually worked, and then further condition on that evidence, right? I think this is perhaps what you're getting to. And maybe the point is that to do that would be trivial. You could just further extend the model, and it would automatically update in the way that you would expect.
Interest of going to lunch, let's thank Zenna and continue the conversation over lunch. And